In the spring of 1901, Captain Dimitrios Kontos and a crew of Greek sponge divers located the wreckage of a Roman-era cargo ship off the coast of Point Glyphadia. Operating at a depth of 45 meters, the divers hauled hundreds of objects to the surface. Initially, the team classified a heavily corroded lump of bronze and wood as standard marine debris. That lump was actually a prochronistic artifact. Before this recovery, the academic consensus regarding mechanical engineering maintained a strict linear timeline from antiquity through the Middle Ages. This 14th century astronomical clock face represents when historians believed the mathematics for complex differential gears first emerged, during the European horological revolution of the 1300s. But the artifact recovered at Point Glyphadia was constructed between the 1st and 2nd century BC. It predates the European clockwork baseline by a gap of roughly 1,500 years. The existence of this single mechanism provides physical evidence that Hellenistic scientific capabilities reached into the territory of early modern mechanics, contradicting the accepted timeline of human progress. When retrieved from the Aegean Sea, the object was a solid, calcified mass of green rock. It sat unnoticed in the National Archaeological Museum in Athens until May 1902. During an inspection, archaeologist Valerio Stais noticed the distinct, mathematically precise teeth of a bronze gear wheel protruding from the crust. The discovery triggered decades of intense academic confusion. The physical evidence of complex gearing directly contradicted every known historical text regarding the limits of ancient Greek technology. In 1951, Yale historian Derek J. DeSalla Price applied modern physics to the problem. He used X-ray and gamma-ray imaging to penetrate the marine calcification without destroying the fragile exterior. This photograph shows fragment A. The scans proved the lump was a dense mechanical calculator. During conservation efforts, it fractured into 82 distinct pieces, exposing a large internal gear and the remnants of 36 others. Numismatic evidence from the wreck, specifically coins found by Jacques Cousteau in the 1970s, firmly establishes the shipwreck's terminus ante quem, the latest possible date of the event, between 70 and 60 BC. This is a bust of Archimedes. Analysis of the artifact's lunar calendar points to an origin in the colony of Syracuse around 205 BC. This links the device directly to the school of Archimedes and the traditions of Babylonian predictive arithmetic. Alternative geographic theories place its construction in Rhodes, aligning with the astronomical theories of Hipparchus, or within the elite scientific library of Pergamon. Penetrating the calcification proved that this was a precision computational device, born from the highest echelons of Greek theoretical science. The internal architecture packs at least 37 meshing bronze gears into a wooden housing measuring roughly 34 by 18 by 9 centimeters, about the size of a modern shoebox. The engineers designed this network to compute a specific kinematic problem, the lunar anomaly. In the 2nd century BC, the astronomer Hipparchus correctly theorized that the moon's orbit is elliptical rather than perfectly circular. Consequently, its angular velocity is non-uniform, moving faster at perigee near the Earth and slower at apogee. The mechanical barrier was severe. The Greeks had to physically model an irregular, accelerating and decelerating ellipse using only perfect concentric circles. This schematic illustrates their solution: pin and slot epicyclic gearing. One gear revolves around another center. Mounted off-center, the pin pushes the secondary slot at a shifting distance, forcing it to physically accelerate and decelerate. This variable velocity turns a dial matching the moon's real-time position. This application of differential gearing to model variable velocity disappeared from the engineering record, only resurfacing in modern clockwork. The pin and slot mechanism represents a physical translation of advanced mathematical theory into moving metal. Translating that geometry into physical bronze required manufacturing tolerances far beyond the standard for a hand-tooled era. The bronze alloy has degraded over 2 millennia into atacomite, a brittle copper chloride mineral formed by seawater corrosion, making the original surfaces fragile. Yet high-resolution scans reveal the precise geometric profile of the remaining gear teeth. They were meticulously hand-cut into equilateral triangles. This visualization illustrates the tooling scale. The manufacturer maintained an average circular pitch, the distance between corresponding points on adjacent teeth, of just 1.6 millimeters. At this scale, teeth require near-zero friction. A microscopic deviation in the triangular cut would jam the entire 37-gear train instantly. The exterior of the device featured front and back wooden doors, covered in dense Greek text. These inscriptions functioned as an operator's manual. They guided the user on how to turn the side-mounted hand crank and detailed the synodic periods of the planets. A synodic period is the exact time it takes for a celestial body to return to the same position in the sky, relative to the sun. The Antikythera Mechanism proves that Hellenistic society possessed the capability to design, machine, and calibrate high-precision analog instrumentation for practical operation. The mechanical reality of this device is rooted in a specific philosophical shift initiated by the Milesian school in the 6th century BC. Philosophers like Thales and Anaximander introduced a conceptual framework historians refer to as the discovery of nature. They argued that the cosmos operates according to explicable, natural laws, rather than the impulsive dictates of a pantheon of gods. In the gears of the Antikythera Mechanism, deities like Zeus and Poseidon are entirely erased. There is no mechanism for divine intervention. This animation represents the device's worldview. It reduces the sun, moon, and planets to pure mathematical objects, bound strictly by predictable, machinated cycles. The machine acts as a historical bridge. It unites the abstract logic of Platonic geometry with the earthly practice of metallurgical engineering. It is the philosophical engine of the ancient world made manifest, a mechanical proof that the universe operates as a predictable system. If ancient engineers could master differential kinematics and 1.6 millimeter tolerances, why did this technology vanish without triggering an industrial era? Hellenistic society maintained a strict separation between logic and practice. Theoretical science was exalted as the domain of the elite, while physical labor and manufacturing were downgraded. Because of this hierarchy, the ancient world lacked a socio-economic imperative to automate tasks. The widespread reliance on human slave labor meant there was no economic incentive to scale up complex mechanical engineering for mass industrial production. Labor was already cheap and abundant. Consequently, the Antikythera Mechanism was an isolated artifact. It was a bespoke plaything designed for a wealthy patron, rather than a prototype for wider industry. Greek logic remained pure but sterile. The brilliant mathematics of the Archimedean tradition fell on the stony ground of a society that could not apply it to everyday production. The Antikythera Mechanism stands as a lonely monument to a scientific revolution that was conceived in theory and proven in bronze, but ultimately starved by the society that built it.